Okay, we started with the problem. We have two areas that parameters are discussed. So what is the assumption is the synchronizing power coefficient is computed from the initial operating condition. That is P12 is 2 per unit, and change of load should be 400 megawatts occurs in area 1. So what is our intention is we have to find out the steady state frequency and the change in tie line power flow. Comment on the results. So these are all the things we are going to find out.
Yes. నీళ్ళుందేనమ్మా
Okay. So we need to find out what is the steady state of frequency and change in tie line flow and comment on the results. So first we have to estimate what is our B1. So B1 is nothing but your power system gain constant 1 by Kp1. For area 1 it is 1 by 50. So 1 divided by 50 means 0.02 per unit megawatt hertz. Likewise B2 power system gain constant B2 is 1 by Kp2 1 by 40 0.025 per unit megawatt per hertz. Next one, we have to find out the regulation for each and every areas. The 3% is given 3 by 100 FR by PR. FR is frequency, PR is your rated MVA. So 3 by 100 into 50 by 2000. So 7.5 times into 10 power minus 4 hertz per megawatt. So when you multiplying with this 2000, that is for turbine output power, you may have 1.5 hertz per unit. And R2 is nothing but 5 by 100. So frequency in area 2 is given as frequency in area 2 is 5%. So 5 by 100 into 50 by 100, which is nothing but a 2.5 into 10 power 3. When you are multiplying 1000, it is 2.5 hertz per unit megawatt. So next is your change in disturbance power D1. So 400 megawatt disturbance is given. So 400 by 2000.2. So disturbance 2 is not given, so it is 0. And next one is beta 1. So beta 1 is nothing but B1 plus 1 by R1, which is equal to 0.02 plus 1 by 1.5. The value is 0.687. Likewise, beta 2 is beta B2 plus 1 by R2. You know the value for B2 as well as R. So 0.025 plus by 2.5, 0.425. The A12 is nothing but ratio of PR1 by PR2, the MVA rating of both the machines. So 2000 for PR1, 1000 for PR2. So change in frequency is nothing but minus of del P2 PD2 plus A12 del PD1 divided by beta plus A12 beta 1. So del PD2 0 here, A12 is 2, del PD1 is 0.2, beta 2 is 0.425, A12 is 2 again, beta 1 is 0.68. So change in frequency is minus 0.2224. So the overall system frequency should be F0 plus del F. So 40 hertz plus minus 0.2224. So 49.777 hertz. So next we need to find out what is our tie line power, the starting condition. So So we have the expression beta 1 del PD2 minus beta 2 del PD1 divided by beta 2 plus A1 to beta 1. We know all the values, substitute it, and you may get minus 0.0472 per unit. So multiplying with the first power, just 2000 MVA, we have 94.52. So alternatively, we can estimate with the help of beta 2 into del F. So beta 2 is minus 425 and del F is minus 0.24. So it is also minus 94.52 megawatts. So both are same. And the next one is change in generation of the area 1 del PG1 minus del F by R1. So del F is minus 0.2224. Already in the formula we have minus. So minus into minus plus divided by 1.5. So 1.494 per unit. In terms of megawatt, we have 296.5 megawatt. So likewise for your area 2, del PG2 is minus del F by R2. So 0.224 by 2.5, it is 88.96 megawatt. So corresponding power we have to multiply 2000 here, 1000 here. The step is skipped here. So next one is change in disturbance power for area 1 as well as area 2. Del PD1 is B1 into del F. B1 we know 0.02. The del F is minus 0.2224. You have minus 8.896 per unit. Likewise for your area 2, B2 into del F. So the value is minus 5.56 megawatt. So change in total load is minus 14.14456 megawatt. So what is the conclusion we obtained as? So 99.42 megawatt flows from area 2 to area 1 and 88.96 megawatt come from the English generation in area 2 and 5.56 megawatt come from the reduction area 2 due to the change in frequency drop. So if you are changing the frequency, the power should be considerably drops. That is the conclusion we obtained on the problem. Next one is two identical areas are interconnected by the weak tie line. If the two areas of the uncontrolled type find the nature of dynamic response following a disturbance in either area in the form of step change in electrical load. The parameter of two identical areas are as under. So regulation R is 4 hertz per unit megawatt. Inertia constant H is 5 seconds. Damping coefficient B is 0.05 per unit megawatts per minute. Nominal frequency is 50 hertz. Assume that the tie line has a capacity of 0.1 per unit, 10% of area capacity, and is operating at a power angle of 45 degree before the step change in load. So let us find your alpha and omega n first. So alpha is nothing but f0 by 4h p plus omega r. So f0 is 50, inertia constant is 5, so 4 into 520 into b is 0.05 just given in the problem itself plus 1 by r. R is 4. So alpha is 0.265 and the T12 that is tie line is your P max 12 by PR cos del I minus del 2 0. So it is 0.1 cos 45, 0.0707. And omega n square is nothing but 2 pi T12 F0 by H. So 4.4422. So if you are taking the square root for omega n square, you may have 2.10766. So here alpha is less than omega n. So the dynamic response will be damped oscillation type. And the angular frequency will be omega d equal to omega n square minus alpha square whole square root. So if you are substituting and solving, you may have 0.2.0367 radians per second. That's your omega oscillation frequency. So next topic, three more topics we have in the tie line, the frequency bias control. So if we are operating a single area or multiple area, so probably you may having the connection or a tie error should be happening. So due to the tie error, you may have the frequency affected. So that frequency affection, how it happens, we are going to deal now. So that is the tie line with the frequency bias control. So the persistent static frequency error is intolerable in a single control area case. So the error should be occur more and more in the single area. Static frequency error is intolerable, and a persistent static error in tie line power flow called inadvertent exchange, IAE. So it means that one area would have to support the other on a steady state basis. So if you are interconnecting one area to another area, it should be purely dependent on one system to another system. So this is the without a dotted line, this is the actual system. So the dotted line shows your tie line power flow. So the when you have connection of the tie line power, the system becomes more complex, and the considerably you have the more number of errors. So obviously the performance of the power system is affected. So with computer based tools we can solve these problems. So for this problem we can overcome with the help of state space analysis. So we have to apply the matrix theory. Thus in state space we have to apply our variables. So if you are applying state space variable format, and the computation should be simple, and you can solve easier. So that is our intention of the forthcoming topics. Whatever we are obtained in your S domain and time domain, we are just modifying into your state space analysis. So once you modify into your state space analysis, the variables becomes it is compact. We are infused in a block. So principle of tie line bias control. So the line bias control is also known as pool operation. So all operating pool members must contribute their share to frequency control in addition to taking care of their own net interchange. So in single area it is not in two area, we have to conceive the arrangement of area one responsible for the area two. So the frequency reset, everything is depends on one system to another system. So ACE1, which is equal to del F1, as well as ACE2 and del operation del beta 2. So the AC would feed via slow integrated respective to the speed changes. So the arrangement is not good. As I said earlier, the arrangement is more complex. வந்து பாத்தீங்கன்னா பார்க்கும்போதே தெரியும் இதை நம்ம சால்வ் பண்றது ரொம்ப கஷ்டம். பிளாக் டயக்ராம் ரிடக்ஷன்லயே சால்வ் பண்ணா கூட சிஸ்டம் இஸ் சோ காம்ப்ளெக்ஸ். நிறைய மேத்தமெட்டிக்கல் 4 to 5 pages ஆகும் சால்வ் பண்றது. உங்களுக்கு ரெஸ்பான்ஸ் இருக்கு. ஸோ அதனால நம்ம என்ன செய்யறோம்னா அந்த கண்ட்ரோல் ஸ்ட்ராட்டஜி, இதை வந்து நம்ம ஒரு கண்ட்ரோல் ஸ்ட்ராட்டஜியா வந்துட்டு I can name as line bias control. So the main intention is one area should contribute to other area. So they have to share their frequency. For example, the area 1 is 50 hertz, area 2 is 48 hertz. So the first area contribute to the second area. That is second area is lagging of frequency. They may contribute one area to other area. Second area is leading, first area lowering, means they contribute. So based on the requirement, they are purely depending on one system to another system. Next one is the determination of tie line with the frequency based control of two area system. So the same principle applying here. They contribute to share the frequency control, own net interchange. So yeah, here everything is integrated here. The incremental power flow, the incremental speed change, everything should be your increment. The steady state, in order to make our steady state error, should be 0. So this is AC1 is, that is area 1, del P tie 1, B1 del F1. So B1 is nothing but area frequency bias. Similarly for area 2, AC2 is del P2, B2 del F2. So what I am trying to do is I just applying Laplace transform for both equations. So AC1 of S plus del P tie 1 of S plus B1 del F1 of S, as well as AC2 of S is del P tie 2 of S plus B2 del F2 of S. So the complete block diagram already represented. So speed changer commands are del PC1 and del PC2. Here it is minus K11 integral of del P tie 1 plus B1 del F1 dt. Likewise, del PC2 is minus K12 integral del P tie 2 B2 del F2 dt. So 2.5435. So K11 and K12 are integrated gains. The constants B1, B2 are the frequency bias parameters. So the minus sign must be included because of increase of generation, either if it's frequency error or tail end increment is negative. So both powers I am just incremented in your negatives. And next one is steady state response. So the step in change in loads, then PD1, PD2 simultaneously applied in areas 1 and 2 respectively. So when we are applying the steady state conditions, the input signals must be 0. So del P tie 1 plus B1 del F1 equal to 0. Likewise, del P tie 2, B2 del F2 is 0. So we can easily find out your del F1 minus del F2 is 0. And the del P tie 1 divided by del P tie 2 is minus A12. It's a constant. So 5, 6 and 5, 7 are satisfied only for when del P tie 1, del P tie 2 equal to 0, or otherwise del F1 equal to del F2 equal to 0. So under steady state condition, the change in tail end power and frequency of each area is 0. So next is my state variable model. State variable model. Optimal linear regulator. Overall design results in a controller that minimizes both the transient variable oscillations and control effects. So it depends on the availability of the system. We can design the dynamic analysis. So the dynamic analysis is performed easily with the help of your state space analysis. So I have my controlled input del PC of S. I have my disturbance del PD of S, and I am having my output del F of S. So you are having your governor constant, turbine constant, and a P constant. So three types of proportionality constants you have in your state variable model. So we are performing for our single area. Two area பண்ண முடியாது, ரொம்ப காம்ப்ளெக்ஸா இருக்கும். So we are just performing for our single area. So your governor and turbine வந்து constants I am keeping to 1. So I am applying a Laplace transform for your turbine generator, your F del PV of S is 1 by STG, del PC of S 1 by R del F of S, and del PT of S is 1 by 1 plus STG del PV of S. Similarly, for L del F of S is KP by 1 plus STP del PT of S minus del P of S. So we can rewrite the equations of 606162 as del P of S F into dg del P of S, just multiplying, minus del PC of S as 1 by R del F of S. Likewise here, del PT of S S into TT del PT of S is equal to del P of S. Third is del F of S. I am just bringing the term to the left hand side. S into TP del F of S. So KP del PT of S as KP del PT of S. So once again, you may write the equations in your time domain format. That is del PV is TG d del PV by dt as del PC minus del F by R. Second should be del PT dt d del PT by dt del PV. A similar manner, del F plus dP d del F by dt Kp del PT and Kp del PD. So this is our governing expressions for turbine, generator and prime mover. So we can define our controlled input del PC வந்து நான் U ன்னு எடுத்துட்டேன் for the ease of convenience. அதே போல disturbance factor del PD வந்து நான் P ன்னு எடுக்கிறேன், capital P. ஸோ அப்படி எடுத்தோம் அப்படின்னா in domain form that is d del PV by dt வந்து minus del PV TG minus del F RTG plus Q by TG ன்னு வரும். அது அந்த ஈக்குவேஷன்ஸ் அப்ளை பண்ணோம்னா அதே போல d del PT by dt del PV by dt minus del PT by dt. Last variable வந்து d del F by dt Kp by dP del PT plus del F by dP plus P into Kp by dP. So these three variables are state variables. So I can state these three variables as state vector x. So the x should be represented as x1, x2, x3. So x1 is del PV, x2 is del PT, x3 is del F. So here I am having in the differential form. So x1 dot should be your del PV. This the d del PV by dt is x1 dot. The d del PT by dt is x2 dot. The d del F by dt is x3 dot. So first equation paranga. So in first equation we have del PV minus 1 by tg into del PV. அதே போல வந்து பாத்தீங்கன்னா PT வந்து இல்ல ஃபர்ஸ்ட் ஈக்குவேஷன்ல, ஸோ 0. அண்ட் F வந்து பாத்தீங்கன்னா 1 by RTG மைனஸ். அதே போல வந்து U வந்து G இருக்கு, G is nothing but U here, so 1 by TG times of your G. Second equation வந்து del PV by dt minus del PT by dt. del PV வந்து 1 by dt. அதே போல PT வந்து பாத்தீங்கன்னா minus 1 by dt. del F இல்ல 0. வந்து del PV இல்ல third equationல, PT இருக்கு Kp by dP. del F is minus 1 by dP. So இங்க P term இருக்கு plus Kp by dP. So the equation should be in the form of x dot equal to Ax Bu gamma P ன்னு இருக்கு. சரியா? இதை வந்து நாம வந்து I can write in your block diagram representations. So U on the input, P on the input, X is your output. So I just summed your BU on the TP. So your controlled variable is X dot into TP. Feedback is CA. So it is a closed feedback system of a linear state model. So இதில் வந்து நம்ம economic dispatch controller feed பண்ணிட்டோம் அப்படின்னா I have to introduce my intelligent controller KX. So அப்போ வந்து நம்ம variables வந்து U is control force and P is disturbance force vector. So U1, U2 is del PC1, PC2, and P is P1, P2, del PD1, PD2. And just equating the parameters PC as well as PD. So now the integration of economic dispatch control with LFC. எல்லாமே பண்ணியாச்சு. So economic dispatch வந்து நீங்க எது பண்ணணும் அப்படின்னா the frequency error should be equal to 0. அது கொண்டு வரணும். அப்படி கொண்டு வந்தீங்க அப்படின்னா your economic dispatch should be satisfied. So how it is integrated? So IC1, IC2 இது வந்து up to so number of times வந்து vary ஆகும். So the IC1 is economic dispatch. So integration is nothing but dF1 by dPG1. And second system is dF2 by dPG2. The system is continuous up to dF1 to dPGN. So the time taken is 2 to 20 seconds. And the primary and the response time is order of 1 minute. So it is a terrestrial control loop. not a first order or second order, it is a third order economic research. Here, the digital computer implementation is implementing here. And it collects the informations of your bus data, generator data, as well as your tail line data. Every information that is collected with the help of your digital computer. So every 5 minutes it is collected through your communication channels, telephones, microwave, etc. So for a closed loop control system operation, a digital computer takes place. So the designer have to write the program and feed the variables in the computer. Computer performs the task again and again infinitely. Yeah. So it is a digital computer control system. So அதுக்கு name particular கொடுத்திருக்காங்க computer control of your power system. So இதுதான் the control system. We have ACE and we have the gain of KI by S step input apply பண்றோம். We have your error detector, speed changer, governor, turbine generator. So local ADC, it is the feedback. So PG actual you may have obtained it. So when you connected with your another area, the same system, you have governor, turbine generator, and PG action. So for each and every control system area, we have to connect a intelligent controller like this. So it performs infinitely and records the data, how it performs. So the data should be recorded with the help of this closed loop control system. So the best solution is obtained while you connecting your computers. So this is the economic dispatch control from the area controller. You have the function generator, you have the comparator, integral controller, speed changer. So இது நம்மளுக்கு மேனுவலா நம்ம பார்க்கறது இதெல்லாம் ஸ்பீட் சேஞ்சஸ் நம்ம தான் மாத்துறோம். அதே போல வந்து ஏரியா இன்டெகிரல் கண்ட்ரோலர். These are all the economic dispatch control equipments. So up to this, I completed my number 2. That's your real power frequency control. அதை வந்து நம்ம வந்து கம்ப்ளீட் பண்ணிட்டோம். So real power frequency controller, we are completed. So I just brush up to what are the topics we are discussed so far. So first we have the low frequency control case of the single area system. ஒரே ஒரு ஏரியாவுக்கு வந்து நம்ம என்ன பண்ணிருக்கோம் அப்படின்னா we obtained that steady state and static response, dynamic state response கண்டுபிடிச்சோம். Both your controlled case as well as controlled uncontrolled case. So based on this general model only, we obtained all the analysis. So இதெல்லாம் நம்ம வந்து static analysis perform பண்ணோம். For the uncontrolled caseல del PC வந்து 0 பண்ணிட்டு del PDS மட்டும் வச்சுட்டு உன்னுடைய ட்ரான்ஸ்ஃபர் ஃபங்க்ஷன் நம்ம எடுத்தோம். அதே போல அடுத்ததுல வந்து del PC வச்சுக்கிட்டு del PDS 0 பண்ணோம். இந்த கேஸ்ல third case PD is 0, PCI we have. இதுக்கு நம்ம வந்து க்ளோஸ் லூப் கண்ட்ரோல் சிஸ்டம் ட்ரான்ஸ்ஃபர் ஃபங்க்ஷன் எடுத்தோம். சரியா? அதை பேஸ் பண்ண ப்ராப்ளம்ஸ் பார்த்தோம். டைனமிக் அனாலிசிஸ். ஸோ டைனமிக் அனாலிசிஸ் அன்கண்ட்ரோல்டு கேஸ் பிசிஎஸ் 0 கிட்ட பிடி மட்டும் வச்சுக்கிட்டோம். ஸோ we have the expressions. And dynamic analysis controlled case, we have PD and the PCS 0. That's based on problems. அடுத்தது we have to two area systems. முதல்ல வந்து பார்த்தது வரைக்கும் single area system. இது இனிமேல்ட்டு வந்து நமக்கு வரதுலாம் வந்து two area system, control area 1 and 2 interconnected by your tie line. So அந்த expressions, derivations எல்லாமே நம்ம வந்து பார்த்தோம் இல்லையா? ஸோ பெரிய பிளாக் டயக்ராம் வந்து இதுலேயும் வந்து நமக்கு ஸ்டாட்டிக் அனாலிசிஸ், டைனமிக் அனாலிசிஸ், கண்ட்ரோல்டு கேஸ், அன்கண்ட்ரோல்டு கேஸ் ஒரு பெரிய ஈக்குவேஷன்ஸ் எல்லாமே வந்து பார்த்தோம். டைனமிக் அனாலிசிஸ் அது பேஸ் பண்ண ப்ராப்ளம். இன்னைக்கு வந்து பார்த்தோம் வந்து டை லைன் வித் ஃப்ரீக்வன்சி பேஸ் கண்ட்ரோல், அதுக்கப்புறம் ஸ்டேட் வேரியபிள் மாடல் ஆஃப் சிங்கிள் ஏரியா சிஸ்டம், அப்புறம் எக்கனாமிக் ரிசர்ச். 11 டாபிக்ஸ் வந்து இந்த யூனிட்ல இருக்கு. ஸோ இந்த பிபிடி மட்டுமே படிச்சீங்கனாலே போதும், வேற எதுவும் நீ எக்ஸ்ட்ரா ஒன்றும் பண்ண தேவை. இந்த 58 ஸ்லைட் இருக்கு இல்லையா, 58 ஸ்லைடு மட்டுமே படிங்க, வேற எதுவும் படிக்க தேவை. யூ மே ரைட் இன் யுவர் யூனிவர்சிட்டி எக்ஸாம் ஆல்சோ. யூனிவர்சிட்டி எக்ஸாம்லயே கேட்டாலும் நீங்க இதுல இருக்க கண்டென்ட் வரலையுமே கொடுத்தாலே போதும், வேற எதுவும் எக்ஸ்ட்ராலாம் படிக்க தேவை. you have any doubts or clarification? இதுக்கப்புறம் 2 வாரம் கழிச்சு தான் நான் உங்ககிட்ட 4th யூனிட் ஆரம்பிக்கும் போது தான் வருவேன். சரியா, இதோட செகண்ட் யூனிட் வருது. நீங்க டவுட்ஸ் இல்ல வேற ஏதாவது இருந்தா கேட்கறதுனா கேட்கலாம். ஏதாவது டவுட் இருக்காப்பா? மறுபடியும் சொல்றேன், ஃபைனல் இயர்ஸ் அட்டெண்டன்ஸ் ரொம்ப லேகா இருக்கீங்க. அட்டெண்டன்ஸ் அப்புறம் குறைஞ்சதுன்னா உங்களுக்கு ஃபைனல் எக்ஸாம் அப்பியர் ஆகாத மாதிரி ஆயிட போகுதுப்பா. நீங்க அவ்வளவு தூரம் இந்த கோவிட் சுச்சுவேஷன் இது பண்ணிட்டு அட்டெண்டன்ஸ்னால எக்ஸாம் எழுத முடியாத மாதிரி போயிட போகுது. அதை பார்த்துக்கோங்க.